Social spiders are spiders that live in groups, which is actually really interesting because everybody's familiar with most spiders being very individualistic, even the stories that sometimes the females eat the males, although that's for the most part occurs but only rarely. But there are some species where they actually live together in single communal webs, so you can have like some dense three-dimensional web, and then you have all sorts of individuals there. Sometimes it may just be a single family. Other times you can have dozens of individuals belonging to different families. And in some species you can actually have these colonies grow for multiple generations until they may cover the whole crown of a tree, and you can have tens of thousands of spiders together living in these groups. And then they help each other in multiple ways. They build these nests together, they maintain them together, they also help each other in capturing prey, they share their food, and they also have communal brood care. So when you see the individuals taking care either of the egg sacs or taking care of feeding their offspring, it may or may not be their own offspring, it's just communal brood care. And with social spiders, there is this very clear geographical pattern that I think provides hints as to why they may be social. So the social species only occur around the world tropics. They occur in different spider families. And then within any one region, say in South America where I do my work, these latitudinal patterns, so you find them in the lowland tropical rainforest, you lose the social species as you go up in latitude, but you also have a similar pattern as you go up in elevation. So you move up in elevation, and where you had social species, at some point they are just no longer there. So the geography of the spider sociality is interesting because it can give us ideas as to why it is that they are social where they are. So there are two different patterns there that need to be explained. One is, why is it that the social species disappear from higher elevations and latitudes? And the other one is, why is it that the subsocial species, the ones with the single family groups, do not happen in the lowland rainforest? And so we have separate hypotheses to explain those two patterns. So the question of why is it that the social species do not happen at higher elevations or latitudes? Our original hypothesis was that perhaps there is just not enough food. These spiders eat insects that fly through their webs, so they make these three-dimensional webs, and then you have webbing going up, and then those webs intercept insects, and then those are what they use as food. And we thought, well, at these higher elevations, maybe there is just enough food. And this is the hypothesis that we set out to test. We set up traps to measure how many insects are flying through an area in a given period of time. We also measured the insects, and we did this at different elevations. So our original hypothesis for explaining why the social species did not occur at higher elevations or latitudes had to do simply with the amount of food. We thought there is just not enough food at these higher elevations to support these very large colonies. And that turned out to be wrong, because at some of the high elevations there was actually plenty of insects. But what it turned out that the issue was not the total biomass of the insects, but the size of the insects. So even though there were lots of insects there, most of those insects were small, while in the lowland rainforest, the biomass was the same, or actually in one of our studies, perhaps even slightly less than at this higher elevation site. But there were lots of large insects. And what really mattered was the insect size, not the total abundance of insects. And even though our original hypothesis was not supported, the new hypothesis that came out of our research was actually a lot more interesting. So what we realized is that as the colonies get larger, like any three-dimensional object, the surface to volume ratio goes down. So there is less surface for any given volume. And these colonies, these webs are intercepting insects, so the surface is important for the number of insects that are going to contact those webs. But the number of spiders in these colonies is proportional to the volume of these webs. So as the colonies get larger, there is less surface per spider, and so that means there are fewer insects per spider entering the webs. So if we were to plot the number of insects as a function of colony size, we would predict that there would be fewer and fewer insects as colony size increases. And that's exactly what we find. And this is surprising because then we have these colonies with tens of thousands of spiders, and they are still together even though they are getting fewer insects per capita. But if they are in an area where there are lots of big insects, what happens is that as the colonies get bigger, they capture bigger and bigger insects. So fewer but bigger insects that makes up for the number. So there are multiple things that one can do with social spiders that are really interesting. Following up a little bit on the story of the geographical distribution, we now have produced some maps using world data on climate to try to sort of show this pattern of correlations, and with precipitation, for instance, or temperature, or other things that may be correlated with insect size. And we are planning to develop some mathematical models to show how these different factors may explain in a more rigorous way, in a sense, the distribution of these spiders in these different areas.